Hello and welcome everybody to the 11th lecture of the Electroweak Instructions to the Standard Model of Particle Physics NPTEL course. And as we have been doing that, we have been looking closely into the Dirac equation and its solutions. We have done the particle-like solutions and anti-particle-like solutions in details. And today we are going to first take a quick look into the possibility of transforming one of these particle-like solutions into one of those antiparticle-like solutions. That will be an interesting thing, and then we will actually take a detailed look into the spin once more. And as I promised that we didn't say everything about the spin quantum number or the spin states, eigenstates that are there in the Dirac solutions. So we are going to take it up and define something called helicity. So those are very interesting things which will be required as we progress. So let's get started. So let's first remind ourselves of what we did for the antiparticle like solutions, and you remember for both particle and antiparticle like solutions we essentially encountered or found out that there are 4 particle like solutions, 2 positive energy and 2 negative energy, and similarly for antiparticle solutions there are 2 positive energy antiparticle solutions, 2 negative energy antiparticle solutions, and we kind of agreed that these are not all independent. So therefore we choose to usually work with 2 positive energy particle like solutions and 2 positive energy antiparticle like solutions, as you can see in the screen. Then we sort of said that for the antiparticle cases, what kind of operators that we can think of, are they exactly the same as those which operate on the particle like solutions? The answer is no, just because of the fact when we take the Hamiltonian operator operate on the antiparticle solutions, it gives you negative energy. And similarly the momentum operator, the standard momentum operator, when it acts on the antiparticle like solution, it gets negative momenta. That's anyway the mandate, but the point is if you have to extract the energy associated with the antiparticles, then essentially you have to take a negative sign on top of that Hamiltonian operator. So therefore we sort of devised or said that the Hamiltonian operator which will act on the antiparticle like solutions should be minus I del del t, and the momentum operator will be I del cross. Now if you flip the sign of momentum, of course the sign of the angular momentum operator will change to minus L, and therefore it will be problematic for us to kind of conserve the HD commutation with the J, which is L plus S equal to 0, unless we change also the spin operator with a negative sign. So therefore we said that okay, all right, the spin operator that will act on the antiparticle like solutions will also have a minus S explicitly, and that's what gave us that if you operate it in V1, then this will give you spin up solutions plus half eigenvalue, and if you operate it in V2, this will give you minus half or spin down kind of solutions. So this is what we actually did so far. Now the question that we would like to take up is that we know that whenever we talk about antiparticles, then there is one important property that we actually assign with the antiparticles is not only the negative energy, negative momentum, but also the electromagnetic charge. Say for example, electron, its antiparticle is called positron, which was discovered in the experiment through its motion under the magnetic field to go in the opposite direction, and that's how it actually possesses 1 plus unit of electromagnetic charge, contrary to the electron which possesses 1 unit of negative electromagnetic charge. So therefore we really have to bring in the interaction of these electrons with the photon or electromagnetic field, which is proportional to its electromagnetic charge. Unless we bring that term into the Dirac equation, we cannot really utilize this criteria that electron and positron possess opposite electromagnetic charges. Now how to do that? Now we know from our electromagnetism, classical electromagnetism rather, that the motion of the charged particle in an electromagnetic field, for which energy will now have an additional counterpart which will be proportional to minus q phi, right. So E goes to E minus q phi, and similarly the momentum will also have an additional piece which will be proportional to the vector potential A and also proportional to the electromagnetic charge q. So E goes to E minus q phi and P goes to P minus q into A. Now if you constitute a 4 vector P mu which comprises of E and P, then this you can say that this p mu basically transforms to p mu minus q a mu, where a mu actually has this components of phi, scalar potential, and the vector potential A. Now, it turns out upon quantization, this is the piece, this is the field which will be the electromagnetic field, or rather the photon, right. And here the Q stands for the electromagnetic charge of the particle which actually is interacting with the photon field, or mu. Now, if you do write it in terms of operators, we know that P can be written as minus I del, and what about E? E will be I del del of T, right. So, together you can say that this P mu operator, if I have to write, how should I write it? I should write it like I del mu, correct. Now, if I want to change P mu to P mu minus Q a mu, so you can say this I del mu, this actually goes to I del mu minus Q a mu for this minimal coupling with the electromagnetic field. Now, we will do a more rigorous exercise to find out how this interaction can be built between electron and photon, but for the time being we are just bringing this interaction in an ad hoc manner. Now, what we are going to do, that we are going to replace this I del mu, which has been replaced by I del mu minus Q a mu, into the Dirac equation. So, what was the Dirac equation? The Dirac equation was I gamma mu del mu minus m psi equal to 0. Now, if you replace this del mu with or rather I del mu with I del mu minus Q a mu, so then this becomes I del mu minus Q a mu psi, right. Now, I can actually dress up this equation in a slightly different way, and I can rewrite this as gamma mu. I have eaten up the I in some way, so that this equation becomes gamma mu del mu plus I q a mu psi plus I m psi equal to 0. I can write it in many different ways. For example, I can also write it like gamma mu del. Okay. So, now the point is that if I have to write it for the electron in specific, so for that this Q, the electromagnetic charge, is minus E. This is the charge of an electron. Q is equal to minus E. So, I am going to replace that here, and with that this equation for electron becomes gamma mu del mu minus I e a mu psi plus I m psi equal to 0. So, once again, to kind of recapitulate, the first equation I gamma mu del mu minus m psi equal to 0 was the equation for a free electron, right, which was not talking to anybody. But now this equation that we have come across, this is the equation for the electron when it is actually interacting with the photon field or the electromagnetism, right. Yeah, and then this equation can also be written in terms of I gamma mu del mu minus I a mu psi minus m psi equal to 0. You can put the I anywhere that you want, of course, in a judicious way. So, this is basically the replacement of del mu going to del mu minus I e a mu for electron when it is talking to the electromagnetic field, but the way that we have bring it in, it is a ad hoc way of doing it. Nevertheless, we will actually do a more judicious way of kind of bringing it later that will show. Now, the question that I would like to ask is that what will be the corresponding Dirac equation if I have to write it for the positron, right? Now, as we just said that for the positron, I know that a minus electromagnetic charge becomes plus electromagnetic charge, or so to say minus E becomes plus E. So, what exactly this equation will then become? This equation, if you look into, this was gamma mu del mu minus I e a mu psi plus I m psi equal to 0. So, I will just replace this minus I e a mu with plus I e a mu, and I am also calling the field or the wave function to be psi prime, which describes the case of positron wave function, and that is actually the psi prime. So, the equation becomes gamma mu into del mu plus I e a mu psi prime plus I m psi prime equal to 0. So, this operator, the interaction operator that we wrote for the electron to change from del mu minus I e a mu becomes del mu plus I e a mu for the antiparticle or for the positron. Now, let us do one exercise, that let me take a complex conjugate of this equation. Okay. So, this is the particle equation that we actually have, and what I am going to do, that I am going to take a complex conjugate of this equation. So, what it becomes, gamma mu becomes gamma mu star del mu, or rather this equation, I may say that this equation I am going to do del mu minus I e mu, what it becomes? It becomes del mu plus I e mu, this is the complex conjugate, and psi becomes psi star, and this plus I m psi becomes minus I m psi star. Okay? This is equal to 0. What I am going to do, that I am going to multiply this equation from the left hand side with minus I gamma 2. Now, why I am going to do this is something that will be apparent in a moment, but let us do that at the first go. I am multiplying this whole equation, this above equation which we obtained for the complex conjugate of the particle or the electron equation, by minus I gamma 2. क्या होगा फिर? This is minus I gamma 2 gamma mu star del mu plus I e mu psi star, and this will become minus m gamma 2 psi star equal to 0. So, this is what happens after multiplying with minus I gamma 2. Okay. Now, what exactly we are trying to do? We are trying to ask this question, as I said just before, that we are trying to correlate this antiparticle wave function psi prime to the particle wave function psi if there is a transformation that we can devise. So, that is what we are trying to look into. So, in that process we have first taken a complex conjugate multiplied with minus I gamma 2 from the left hand side. Now, we note certain properties of the gamma matrices in the Dirac-Pauli representation which we have been using, and that says that the gamma 0 star is actually gamma 0, gamma 1 star also becomes gamma 1. However, gamma 2 star actually changes sign to minus gamma 2. Okay? On the other hand, gamma 3 star also remains gamma 3. Further, we can also observe that there is an anti-commutation relation between gamma 2 and gamma mu, so that minus gamma 2 gamma mu becomes actually gamma mu gamma 2. So, basically when you change the sign, the position of gamma 2, it flips the sign. Okay? When you change the position of gamma 2, so minus gamma 2 gamma mu becomes gamma 2 gamma mu for mu not equal to 2. Of course, when mu is equal to 2, there is nothing to anti-commute because it is the same matrix multiplication. Now, if I use these facts, then there is an interesting thing that we observe, that we can bring this I gamma 2 which I multiplied from the left, I can bring this gamma 2 on the other side of the gamma mu star becomes gamma mu, and gamma 2 I can bring on the other side with an exchange of signs. So, therefore, using this, what we can do, we can rewrite this equation like gamma mu into del mu plus I e mu, and inside the bracket I basically have I gamma 2 psi star. Okay? And this last term, that also I can trade off this minus 1 to be I square and take one I m to be common and outside, and inside the bracket I have I m gamma 2 psi star. Now, this is something interesting, that if I sort of define now that a psi prime which is equal to I gamma 2 psi star, if I define this, what happens? This above equation basically boils down to something like gamma mu into del mu plus I e mu psi prime plus I m psi prime equal to 0. Now, compare this equation with the equation that you wrote for the positron. So, you argued that the equation for the positron was essentially gamma mu into del mu plus I mu psi prime plus I m psi prime equal to 0. So, this is essentially identical equation with that of the positron. So, I can then claim that this transformation that I did, that psi prime is equal to I gamma 2 psi star, this defines a transformation from an electron to an positron wave function. Okay? And you can also say that this is a charge conjugation operation where C psi is essentially psi c, which is I gamma 2 psi star. But remember that this definition of the charge conjugation that we have done here is very specific to the representation that we have used. Now, I have said that when you take the charge conjugation, basically that electron becomes positron, that's something that we established. But we have already found out the particle and antiparticle solutions explicitly. So, we can check what happens when we take the charge conjugation operator, which is namely I gamma 2 psi star, when we explicitly use the Dirac Pauli representations. So, for example, psi 1 was what? This was actually u1 EP e to the power I p dot x minus et. Now, what happens if I take C psi 1, which is psi 1 c, which will be in turn I gamma 2 psi 1 star. So, therefore, this will become I gamma 2 u1 star into e to the power minus I p dot x minus et. You already see in the phase space part, it is already started to resemble that of the antiparticle case. Now, I have to explicitly find out what is I gamma 2 u1 star here, and that is simple. This is simply a matrix multiplication. I gamma 2 kya hai? 0 0 0 minus I etc. etc. You just write it from the very definition. What is u1 star? Let us go back to these definitions that we have come across, or rather what we have found out. So, this was u1 10 pz by e plus m, px plus ipy by e plus m. Let us replace this with u1 star. क्या होगा? This is going to be 10 pz by e plus m, and px plus ipy becomes px minus ipy when I take the complex conjugate, right. So, this is what happens, and now if you do the matrix multiplication, it simply becomes px minus ipy by e plus m minus pz by e plus m 0 and 1. Do you remember what kind of spinor this is? If you go back to your found out spinors, and this is exactly what we wrote as V1, right. So, V1 is Px minus Ipy by E plus m minus Pz by E plus m 0 and 1. So, this is exactly V1, and so therefore, you can conclude that I gamma 2 U1 star essentially is taking me to V1. So, therefore, in general, when you are taking this transformation of C psi 1, this is actually taking you to V1 into e to the power minus I p dot x minus et, correct? And this is precisely the antiparticle wave function that we wanted to find out. So, this charge conjugation indeed on the particle spinor takes you to the antiparticle, and this is not only true for psi 1, this is true for psi 2, and it is also true actually for the antiparticle cases, and these are all the things that you are actually going to do as a homework. So, please check that when you take C psi 2, this is going to give you V2 into e to the power minus I p dot x minus et. So, therefore, we can define a charge conjugation which will take you from the particle to antiparticle like solution. Now, with this, let us move ahead and get back into the spin which we actually talked about to some extent. So, what was the spin operator that was defined on the Dirac spinors? It was basically half of sigma 0 0 sigma, where sigmas are the Pauli spin matrices, and you remember that this definition of S will actually make the Dirac Hamiltonian, free Dirac Hamiltonian commuting with the total spin, which is L plus S, that is going to give you 0. What was the Sz? This is half of sigma z 0 0 sigma z. What was actually your sigma z? Now, all of you remember that sigma z is something like 1 0 0 minus 1. So, what will become this matrix, this Sz matrix which will act on the Dirac spinors, this will become 1 0 0 minus 1, this is 0 0 0 0. Similarly, here 0 0 0 0, this is 1 0, this is 0 0 0 minus 1, right. Now, Consider the Dirac particle spinors at rest when they are at 0 momentum. Okay. Then you remember U1 is simply 1 0 0 0 and U2 is essentially 0 1 0 0. And you also have seen that when you take a Z operator on acting on U1 E0, what exactly this is going to give you? This is going to give you an eigenvalue of plus half unit. What happens when AZ acts on U2? This is going to give you the minus half eigenvalue. Okay. So, therefore, these are the two so called U1 and U2 are therefore spin up. So, this is your spin up and this guy is the spin down states. But remember, this eigenvalues that you have found out is strictly for the 0 momentum case. Now, consider the antiparticle solutions. What is the p equal to 0 state of V1 E0? This will be simply 0 0 0 1 and for V2 this will be 0 0 1 0, right. So, this is something very easy to check and you should do it once more. Now, how can we define the spin operator acting on the antiparticles? Just because we want to keep the Dirac Hamiltonian commuting with the total angular momentum and the orbital part of the angular momentum, because of minus p have already taken up a negative sign. So, therefore, I had to bring one explicit negative sign on the spin operators also. So, now if you operate minus Sz on V1 E0, what exactly this is going to give you? You can check that this is going to give you plus half V1 E0, and when you take minus Sz on V2 0, this is going to give you minus half V2 E0. So, therefore, we also identify V1 and V2 are essentially the spin up and spin down antiparticle states in the 0 momentum limit. However, this is now a very important point, that if you take the generic matrices, the eigenstates of the Dirac Hamiltonian for p not equal to 0 case like U1 EP, U2 EP, if you take these matrices and operate as Z on them, you will find out that these are not the eigenstates of Sz anymore. When you go to p not equal to 0 limit, they are not eigenstates of Sz in general. So, this is something that you must check explicitly. Okay. Now, so there is a bit of issue. I mean, the eigenstates that we are finding is only possible in p equal to 0 limit. Is it the only case that is giving you the eigenstates, or there is something more that we can say? For that, let us try to take this limit when the momentum is actually along the z direction, or you say that p is actually plus minus of p z hat. Okay? That means you can treat px and py is equal to 0 and take pz equal to plus minus p. In this limit, what happens to this Dirac spinors, the solutions which are the eigenstates of Dirac Hamiltonian, what happens to them? Let us try to take a look into this. So, U1 is 1 0 pz by e plus m, etc. So, what happens in this limit when px py equal to 0 and pz equal to plus minus p? This becomes 1 0 pz is plus minus p by e plus m, and this quantity is absolutely 0. What happens to U2? This becomes 0 1, this is once again 0, minus pz means minus plus p by e plus m. What happens to V1? Once again the first quantity in the limit px py going to 0 is identically 0. What is the second component? Second component will be minus plus p by e plus m, this is 0 and 1, and V2 finally this is plus minus p by e plus m. This second term is absolutely 0, this is 1 and 0. Now, let us once again operate this Sz on this U1 which is in the limit when U1 with E 0 0 plus minus p. This basically means that I am referring to the spinor when the motion is along the z direction. So, if you do this exercise, it is a simple matrix multiplication once more, you will find that this is once again an eigenstate of Sz and giving you an eigenvalue of plus half. So, this is once again you can check for all of them and you can see that when the motion is actually along the z direction, these spinors are eigenstates of Sz, like Sz u1 is plus half u1, Sz u2 is minus half u2, minus Sz v1 which is plus half v1 and minus Sz v2 is essentially minus half v2. Once again I will urge you to check all of them. So, u1, u2, v1, v2 are essentially spin up and spin down eigenstates of Sz when the motion is along the z direction. So, pictorially you can say that when s is equal to half, the spin is actually projected along the direction of the motion. When s is equal to minus half, the spin is projected opposite to the direction of the motion, and this is what is shown in this picture. If you actually assume that the spin arrows are like this and this arrow defines the direction of the motion. So, this is how the way that you can draw u1 and u2. Now, if you have to draw the case of v1 and v2, how can you do that? First, the direction of the motion is by this arrow, then this is s equal to half, that means spin is projected along the direction of the motion, and for v2 this is actually giving you the spin projected opposite to the direction of the motion, and this is how you should draw this. Okay. However, this is once again something interesting, but however, in general if you calculate the commutation relation between the Dirac Hamiltonian and Sz, you can clearly see that this does not commute. This gives you I alpha cross Pz. So, this is very well, we have done this exercise, so you can do this very well at home. So, please check this once more. But what does it say? It basically says that it is not possible to define simultaneous eigenstates of the Dirac Hamiltonian and Sz. So, therefore, we need to identify some operator that inherits the spin information, but commutes with the Dirac Hamiltonian. Now, we have tacitly already have identified something. So, when the spin is projected along the direction of the motion, that quantity, whatever that we can call, will be having a simultaneous eigenstate with the Dirac Hamiltonian. This brings us to the definition of helicity, and we can say that helicity of a particle is essentially defined by the normalized components of its spin along the direction of the motion, or in a sense you can define H as S dot P by mod of P. Now, S is what? S for us is half of sigma, which is half of the Pauli spin matrices sitting in the diagonal entries of a 4 cross 4 matrix. So, if you have to write the 4 component Dirac, the helicity operator acting on 4 component Dirac spinor, how should you write it? This will be simply sigma dot P 0 0 sigma dot P with 1 by 2 of mod P sitting outside. Now, you can explicitly check that HD actually commutes with sigma dot P. That means, HD actually commutes with the helicity which we have defined, and that is the thing. So, helicity is something which is the closest to the spin that will have a simultaneous eigenstate with the Dirac Hamiltonian, right. So, helicity commutes with the free Dirac Hamiltonian, and hence it is possible to have a simultaneous eigenstate of Dirac Hamiltonian with helicity. But on the other hand, because spin will always be quantized to the values of plus minus half, right. So, the helicity will definitely have eigenvalues of plus and minus half, and you can say that when the helicity is plus half, I can say that this is actually the definition of what I call a right-handed fermion, or in small notation I can say this is RH, and when the helicity is minus half, I will call this to be a left-handed fermion or minus LH. So, pictorially this is similar the way that we actually drew it out before, that the right-handed case, when H is plus half, the spin will be projected along the direction of the motion, and for the left-handed case, when H is minus half, it is actually the opposite to the motion. However, we still have to find the simultaneous eigenstates of the Dirac Hamiltonian and the Helicity operators, which we are going to do. But before that, let me try to see if I can find this Helicity eigenvalues of lambda equal to plus minus half when I have this equation, that this is my eigenvalue equation for the Helicity operator. So, H acting on U giving you lambda U, where U is the eigenstate and lambda is the eigenvalue, and I want to see if this lambda is really plus minus half. And in order to do that, what I do, that I write U in terms of two component spinors as before, with UA and UB, and you know H is 1 by 2 p sigma dot p, etc. And on the other side I have lambda into UA and UB. If I do the matrix multiplication, I have two simple equations, which is sigma dot p acting on UA giving you 2 p lambda UA, and sigma dot p acting on UB giving 2 p lambda UB. Now, how do I show that this gives me lambda equal to plus minus half? There is one mathematical identity which I am actually using, which you can show very easily. This is sigma dot p whole square is equal to actually p square into the identity matrix. So, once again check it explicitly. This is very simple. So, please check it explicitly, where sigma dot p is what? Pz px minus ipy, px plus ipy minus pz. This is a simple matrix multiplication. Now, I have this relation that sigma dot p acting on UA giving me 2 p lambda UA. Let me operate another sigma dot p from the left hand side. Okay. So, this is sigma dot p UA equal to 2 p lambda, just it is a number, so it comes out, and it will be sigma dot p acting on UA. Sigma dot p acting on UA is once again 2 p lambda UA, right. So, this is going to give you, so this is p square, so this is p square into UA into 2 p lambda whole square into UA, right. So, what does it say? It basically says that p square is 4 p square lambda square, or 4 lambda square is equal to 1. That means lambda is plus minus half, indeed the one that we envisaged, right. So, this basically shows that you can have the eigenvalues to be plus minus half. Now, the question is that if U is an eigenstate of HD, then it solves the Dirac equation, and you remember that while we were trying to find out the solutions for the eigenstates of the Dirac Hamiltonian for the particle case, and we also identified that UA, UB to constitute your U, then gamma mu pu mu minus m U equal to 0 was the equation that we tried to solve, and that leads to the fact that sigma dot p UA is equal to E plus m into UB. So, this is something that you have to remind yourself from the previous lecture. Okay. On the other hand, sigma dot p is 2 p lambda if it has to simultaneously solve for the eigenstates of the Helicity operator, right. So, then we can say that UB will be related to UA via this relation, that this is 2 lambda into p by E plus m. But this is UB, but we have to find out first UA, and we have to find UA from this kind of eigen equation, which is sigma dot p acting on UA is equal to 2 lambda p UA. And for that, what we are going to do, that we are going to consider the momentum in spherical polar coordinates, where the x component is p sin theta cos phi, y component is p sin theta sin phi, and the z component is p cos theta. Now, this is something that you all know, right. Now, let us remind ourselves that what was sigma dot p. As you remember, the sigma dot p, this is essentially pz px minus ipy, this is px plus ipy, and this is minus pz, correct. Now, if you put these values, pz is p cos theta, px minus ipy becomes sin theta e to the power minus I phi, px plus ipy becomes sin theta into e to the power I phi, and minus pz becomes minus p cos theta, the p gets cancelled with outside. So, basically this sigma dot p divided by 2p simply becomes 1 by 2 of cos theta, this matrix. Okay. So, this is what we read. Now, the eigen equation was sigma dot p by 2p UA, giving you lambda into UA. Now, what you can do that for UA, you assume this matrix to be having two components A and B, and just write explicitly once again. So, this is this whole quantity into AB equal to 2 lambda into AB, and do the matrix multiplication. If you do this matrix multiplication, what you are going to see that you are going to find a relation between this B and A terms which you actually identified for the entries for UA. Now, if you choose lambda equal to plus half, then I can put it back in this expression for 2 lambda, and this just becomes 2 sine square cos theta I have expanded as 1 minus 2 sine square theta by 2, and sine theta I have expanded as 2 sine theta by 2 into cos theta by 2, and in this way I can cancel 1 sine theta by 2 up and down, and this gives me sine theta by 2 into e to the power I phi by cos theta by 2. So, this is the ratio of B by A, and what I can do that I can say, okay, I can actually choose A to be simply cos theta by 2, and B is equal to sine theta by 2 into e to the power I phi from this ratio. This keeps the B by A ratio that we have actually found out above consistent. And then we adhere to this equation that UB has to be equal to 2 lambda P by E plus M into UA, right. So, therefore, I can say that UB will be for lambda equal to half, this is simply P by E plus M into UA. So, that gives me the full U up matrix, which is actually for the lambda equal to plus half case, and that will simply become what? This will become the first the UA component, which is cos theta by 2 sin theta by 2 e to the power I phi. Then the UB components, this will be simply multiplied with P by E plus M into cos theta by 2, and the last component is P by E plus M sin theta by 2 into e to the power I phi, correct. So, this is basically the U up matrix, and I have found out one spinor which is the eigenstate, or rather it is a simultaneous eigenstate of the helicity as well as for the Dirac Hamiltonian. Similarly, this is for lambda equal to half case, and for lambda equal to minus half, I will just utilize the same B by A equation with lambda equal to minus half, and I found out that the ratio turns out to be minus cos of theta by 2 by sin theta by 2 into e to the power I phi. Once again, that gives me a choice that I can choose my UA to be minus sin theta by 2 and cos theta by 2 e to the power I phi. And once again, let us go back to the expression of UB, which is actually 2 lambda P by E plus M into UA, and here I am going to put lambda is equal to minus half. If you do that, this gives you minus P by E plus M into UA, and with this I am now in a position to write the U down, or lambda equal to minus half, or the left handed particle like solution for the Dirac equation, and what that is going to be minus sin theta by 2 cos theta by 2 e to the power I phi, correct. And now you have minus of P by M, so it becomes plus P by E plus M into sin theta by 2 and minus P by E plus M cos theta by 2 e to the power I phi. So, this is the left handed helicity eigenstate. Similarly, you can do the antiparticle eigenstates also. Just remember that because for the spin operator acting on the antiparticle becomes minus s, so the helicity becomes minus of 1 by 2 p into sigma dot p, and h plus half, that is going to give you minus half v up, and h equal to minus half, that is going to give you plus half v down. So this is an interesting thing. This is something that I want you to do it explicitly. The process is very, very similar, but what we are going to do, that following that same procedure, we are going to find these different components, and finally we have the hv equal to plus half or lambda equal to minus half eigenstate, which we call v up, and that is given by this quantity, this spinor. This is the right-handed antiparticle, right? hv equal to plus half is actually the right-handed antiparticle. Similarly, the left-handed, this is the left-handed antiparticle, this solution is once again is obtained for left-handed antiparticle का solution कैसे मिलेगा? This has to be obtained from lambda equal to plus half solution, which actually gives you hv is minus half. So that's how this nomenclature is v down, and this is this quantity. So with this exercise, what you have, that you have once again gotten 4 helicity eigenstates, and these are u up. Well, I mean, I should not draw this arrow just not to confuse you with the up and down state. So you have u up, you have u down. The u up is the right-handed particle solution, u down is the left-handed particle solution, v up is the right-handed antiparticle solution, and v down is the left-handed antiparticle solution. And in this simplification, what I have done, that we usually choose a shorthand notation of c is equal to cos theta by 2, s is equal to sin theta by 2, and once again this up sign basically means h equal to plus half, and down means h equal to minus half. Okay. So with this, I think I am going to finish today, and we have solved the Dirac equation quite elaborately. Okay. Thank you so much, and stay tuned for the next lecture.